So hi everybody, my name is Vicențiu. I am a software engineer at the MariaDB Foundation. So before I get into details, how many of you have heard of MariaDB before? All right. How many of you have used MariaDB in production before? Okay, not so many people. All right, well, that's fine. I'm going to go through a very brief history lesson. So I assume at least a couple of you have heard of MySQL. It's a pretty popular database system. So it was acquired by Oracle indirectly through Sun Microsystems acquisition. And as a result of this, the creator of MySQL, Monty, did a fork of MySQL and created MariaDB, with the hope of ensuring that MariaDB is always an open database system. And to ensure this, he's also created the MariaDB Foundation, which owns the access to the MariaDB server repository and is in charge of ensuring open collaboration and continuity for the server from now on. And we do this by ensuring that we develop everything in the open. So we code everything in a public branch. People can see the progress as we go along. We don't do releases with features every once in a while and no other information. And because of this, lots of distributions have adopted us as their default MySQL implementation. Quite recently, we've been declared default in Debian 9. So if you actually install MySQL, you get MariaDB behind the scenes. We try to be as backwards compatible as possible. So most of the applications should normally work with, that work with MySQL should work with MariaDB. So the MariaDB Foundation is a non-profit organization. And I have to personally thank Jean-Paul for making it possible for me to be hired by the foundation. He's been kind enough to pay my salary for a long time. And him and amongst other sponsors, Nexity, they ensure that the foundation's mission succeeds. So now let's get into the discussion for today. How many of you own a smartwatch? Okay. I'm a bit surprised, very surprised actually. But nonetheless, the pictures here are from the Vector smartwatch company, which is a company based in Romania. It was acquired by Fitbit last year. But the point is that embedded systems have now become present every day in our lives. And most of these systems have increasingly higher capabilities. You can get a fully fledged system on chip that can run AOS, either Linux, Windows, or some other flavor, that consumes only 5 watts of power when it's at full load, and it has enough capabilities to dwarf some very expensive automation systems. They also, most systems come with a large variety of sensors, and you usually want to store the sensor data within the chip until you have time to move it out to your mainframe or other storage solution. So systems themselves have to keep databases. So the question is, what kind of databases are best for each particular job? And to make an analogy, you could try to hammer in a nail with a screwdriver, or you could try to hammer in a screw, but you're probably not going to be very successful. So the key is to get the right tool for the job. And it's very important that you make this decision early in your development project. And in order to do this, you have to understand a few things. So first of all, you must understand the tools that you have available, what are their strengths, what are their weaknesses. And you must understand how it works with your full system. You can't just look at a tool in a vacuum and see, okay, this is better because it has X, Y, Z features. Maybe you don't use X and Y features, so it's pretty much useless. And other times it's not very clear-cut what kind of system you should be, what kind of tool you should be using. In this case, testing is required. So I've had this use case, and I had to make a decision at some point. Does it make sense to use a more de facto standard for embedded databases, which is SQLite? or try to use a more complex database system. So the use case is like this. We have a highly connected IoT application with lots of sensors everywhere. Think smart houses with maybe 5 sensors per room or more. And all these sensors feed in data constantly. And we need to also monitor what those sensors gave us in the past week or month. So we need to store this. And we don't want our system to eat up hundreds of watts of power just because we want it to be smart. We need to be efficient as well. Especially if you're running in a remote location, you might just have solar power with very small solar panels, so you want to be very efficient with power. So the candidates, well, SQLite is the de facto standard, but obviously I'm working for the MariaDB Foundation, so the other candidate would be MariaDB Server. So the question is, how big does our system need to be to warrant a more complex database management system? SQLite has its features, MariaDB has its features. Do we pay more for extra features or do we not? So to test, I've used 2 storage engines for MariaDB. Storage engines are specialized bits of the code dealing with how to store data. We have 2 general purpose storage engines. One is InnoDB. It's a very old storage engine. It's been under development for a long time now. It supports transactions. And it's thought to be a very good choice in most use cases. However, there's also been another storage engine developed by Facebook, which is now shipped in MariaDB. It's supposed to optimize for solid-state storage, like SSDs. The aim is to store as little data as possible so that we don't wear out SSDs. And I've also looked at SQLite, the candidate. For both servers, I've used the most recent version. I've compiled the versions directly on the device with the best possible optimizations for performance using the compiler that this distribution had at the moment of doing this test. So the hardware was a Raspberry Pi. So why did I choose a Raspberry Pi? Well, because it's one of the, let's say, cheapest systems available. It's also not very powerful, so it's highly representative of a low power, limited resource solution that is not as limited in that it can run a fully fledged OS system. So in this case, we have a 1.4 gigahertz processor with 1 gig of RAM, and I've chosen to use the fastest SSD card, which I could, not SSD, sorry, fastest memory card that I could buy for a reasonable price. It's rated for up to 100 megabytes per second read and 60 megabytes per second write. None of these numbers I was able to hit even remotely close, but that's what the manufacturer says. Oh well. Any questions so far? Does it make sense what I'm trying to test? A few bits about the Raspberry Pi is that it tends to overheat. So the chip itself is not cooled sufficiently if you put load on it. So in order to get it working properly, you have to put heat sinks on it. So I have added those heat sinks. Still, I hit the soft thermal shutdown limit of around 65 degrees. The chip runs at around 1.2 gigahertz when fully loaded. You can think of this like Intel's Turbo Boost technology, so I was okay with this. However, the power supply is a bit strange. The Pi requires 5.1 volts of power. However, because I had lots of losses with the connectors, I ended up cranking the power all the way to 6.6 volts. A bit reluctant because it seemed like the Pi would fry, but it seems like it worked. The power draw is around 1 amp. So we can roughly say we usually use about 5 watts of power. The Pi has support for under voltage, so it will try to keep itself stable as much as possible, but the performance drops significantly. My initial benchmarks show that if you don't power it properly, you get less than half the performance that you would get if you were to power it with a stable power supply. And now I tried to do a benchmark. Unfortunately, there is no universal benchmark for MariaDB that works for both MariaDB and SQLite. We have SysBench, which works for MariaDB and Postgres, but there is no equivalent sysbench driver for SQLite. So I have a bit of a problem because I can't simulate this with already existing tools. So I had to manually write the benchmark myself. I tried to make an educated guess that most of our workload will be inserts, so append only. And we will do range select, so select from a certain timestamp to another timestamp. But those won't happen as often. So with this workload in mind, I simulated multiple test cases. I tried to connect with just one connection to the system, or multiple connections, do multiple inserts in parallel. And I judged the insertion speed when I was maintaining an index for faster lookups, or without an index. Multiple connections poses different problems, especially with SQLite, because you are not allowed to write multiple things at the same time in SQLite. You need to use some sort of timeout protection or busy waiting. So you try to insert stuff, the database says, no, sorry, I'm busy. Then you try again, maybe it works, maybe it doesn't. So it's a bit tricky. There is a setting to SQLite to put a timeout on each transaction. I had to increase this all the way to 15 seconds. So in the worst case, one of your transactions can take 15 seconds or more to complete, which is not ideal for lots of use cases. Now the test data is relatively simple. Just insert the ID of the sensor, a timestamp, and 20 values that the sensor can provide. 5 integer columns and 15 double value columns. Seems like a reasonable estimate. Looking at smartphones these days, they probably have more, but I was happy with this. So the biggest test tries to insert into 20 tables, 2 million rows per table. This is around 80 gigs of data, and we're going to see how fast this can happen. Before we go into write or read performances, let's look at memory usage. SQLite never goes above 70 megs of RAM, whilst MariaDB can be tuned to use up to all the RAM you have available, although not recommended. Stick within 70 to 80% of the limit. I reached the performance peak at around 256 megabytes, so a quarter of the Pi's total memory. Putting it more just didn't do any good. So when it comes to memory usage, SQLite is clearly a better option. So now let's try different ways of inserting data. Either we insert things one at a time, or we try to batch it up in increasingly larger batches to see where we hit the overhead, where the overhead of actually adding inserts is less than the time spent writing to disk. So if we have batches with 100 rows in size, we have a lot of overhead. We spend a lot of time parsing insert statements and not actually doing useful work. As we increase the batch size, we can see that the amount of time it takes to insert 1 million rows decreases. This is also only one connection. I'm not using multiple connections yet. And if we try to maintain an index, we can see that there is some overhead. So these lines are MariaDB's insert performance, and this is SQLite's insert performance. Both cases have a small performance drop-off if you add an index. But as I've said, this is one connection only. So what happens when you have multiple connections? Or actually, I think the next slide deals with multiple connections, but also how performance changes over time. The more data you have, you can see that SQLite starts to lose performance. MariaDB also starts to lose performance. This is mostly because the fuller the SD card gets, the slower the write performance on it. But SQLite has a bigger overhead than MariaDB when you have a lot of data already in the system. So I mentioned before that I'm going to use 2 storage engines for MariaDB. One is SQLite, one is InnoDB, one is RocksDB. There's a difference here, and we're going to dig into this. But first, let's compare SQLite to MariaDB, InnoDB. So SQLite takes around 1 hour to insert 8 gigs of data, or 40 million rows. whilst MariaDB is about 5 to 10% faster. The reason why there is such a small difference here is that initially MariaDB is slow in inserting. It has a warm-up time when things start to get put into memory, and then eventually it speeds up and overtakes SQLite. Also, SQLite has the overhead. When it writes more stuff, it gets slower over time. And now we have RocksDB, which is supposed to be better for SD cards and SSD storage. So why is it slower here? Now, this was interesting, and I spent a bit of time looking at this. And I looked at CPU usage. So SQLite uses at most 33% of the CPU. And this is because SQLite is single-threaded. Our system is single core, so we use one core fully to do the writing, and we have a bit of overhead with communication, which leads us to about 33% usage. Now, MariaDB uses more cores when available. And with InnoDB, we plateau around 66% usage. Most of it is, we do all the processing we can, but we have to wait on for the storage to catch up. So we still have a bit of room for the CPU, but there's nothing we can do because we have to wait for storage. However, RocksDB does compression, and with compression, we have lots of CPU usage. We're almost at 100% for most of the time. So it seems like we're doing useful work there. But there's two problems. One, the Pi is overheating and hitting the soft CPU limit, but that's not the main problem. The main problem comes with how we're using the SD card. So let's have a look at I/O. Well, with I/O, we have a space usage that is the smallest for RocksDB. So compression works. That's perfectly fine. SQLite stores around 8.5 gigs of data for an actual 8 gig database, whilst MariaDB InnoDB stores roughly the same amount, yet we store a bit of extra metadata, so log records, and those eat up about 300 megs, so a bit more data stored there. When it comes to actual data written, the database has to write multiple times for the same data to ensure that in case the system crashes, you don't lose anything from your previous transactions, which is why you can see that InnoDB does double the amount of writes as opposed to SQLite. This is due to InnoDB's double write buffer. So I'm not going to go into details, but we need to do those writes in order to ensure we are crash safe. RocksDB, on the other hand, aims to reduce writes as much as possible whilst ensuring the consistency in case of crashes. And it's doing a decent job here. Better than InnoDB. SQLite is a bit more fragile here, so in case you have a crash, you might lose a few things, but it's still relatively a safe option when you want to do transactional inserts. But now we get to the final column, and look at RocksDB here. It takes way more, it does way more reads than anything else. So why is this? Well, RocksDB, as it keeps adding stuff to the database, it has to compact it to make it smaller. And it needs to read the data back, put it into memory, and write it back again in a compressed form. With all this I/O activity, because the SD card is slow, we have bad performance with RocksDB. Had we had faster storage, or better buffered storage, or even a faster system overall, the numbers that you've seen here would be roughly the same. And we have tested this with faster systems, but when you go to a very low power system, it doesn't work properly. And I haven't plotted the CPU usage graph, but for RocksDB, it looks like this. 90%, okay, we're doing work, then 0%, waiting for SD card. 90%, 0%. And that's a very unfortunate way to use our resources. Right, so this is all about insert performance. Let's go to selects. So if data fits in RAM, RocksDB and InnoDB are faster than SQLite. the caching algorithms for MariaDB are better as long as you give it enough time to warm up. So the first selects are going to be horrible performance-wise. It's about 10 times slower than SQLite. Lots of bookkeeping needs to happen. When we get to a more frequent select statement, we get better performance overall. So the time it takes to do a range select for roughly a week of data, that implies about 1 million rows of selects of data retrieved. If it fits in RAM, then it's very fast. Whilst if it doesn't fit in RAM, all the bookkeeping I told you before, it's not valid. We end up wasting a lot of time reading from disk. SQLite is a lot simpler. All it does is it increases linearly with the amount of data you need to read, which if you're in a memory constrained system, this is the better option. But if you have a fast enough system with sufficient amount of memory, in this case, SQLite, MariaDB is better than SQLite. So conclusions, SQLite overall has a smaller runtime footprint, which makes it ideal for very small systems like smartwatches or phones, but it scales poorly with writes. You can't write concurrently to the database. You only have to have one writer, and that stops all readers also. So it's a very bad performance bottleneck if you want to read more stuff from the system. With MariaDB InnoDB, you can use more RAM to improve your performance, and the write performance is slightly better for larger data sets, but it takes a while until you get to the point where you are faster than SQLite. And if we, as we've seen with read performance, if we have limited RAM, we have very bad seeks, so it's a cost there. With RocksDB, like InnoDB, we have the performance of if we have more RAM, we perform better. If we don't have RAM, we're out of luck. And write performance is also surprisingly worse in this SD card case because we are waiting for the storage to catch up. And also, the nice part is that RocksDB does write less to disk than InnoDB. So if you're at the point where you don't want to use SQLite anymore and you want to go to a more complex system, then RocksDB will probably be a better option. So for a small system, definitely go for SQLite. It scales poorly with concurrent inserts, however, and if your data set is greater than 2 million rows, roughly, it's recommended to investigate other options, because you might find it better for your use case. And as I've said, with faster CPUs and faster storage, a more complex system usually wins because it gives you extra flexibility and better performance overall. That's it. Thank you very much, and if you have any questions.